Hi all, today we start discussing chapter 2. This is the first module. In this video we discuss section 2.1. Section 2.1 consists of a few examples of linear spaces or vector spaces, and one definition is discussed in this section as well. So let us start the examples of vector spaces. I hope you might have seen the definition of the vector space and the basic properties of the vector spaces uh, in your degree classes. So let's see a few examples of vector spaces first. So first we take to begin we take the n tuples of fields, n tuple space. That is what we call n tuple space, and it is denoted by Fn. So this F is any field. Uh, you have seen so many fields like R, C. These two are infinite fields. Then for finite case we have ZP or any Galois field of cardinality P raised to n and all, or any field of finite number of elements P raised to n. I think you will be discuss this Galois field in your second semester. So if we, for example, if we take R2, R cross R, that is denoted by R2, this consists of elements x1 comma x2 such that x1 comma x2 are elements of real numbers. Okay, so this form a vector space. I am not going to verify all the axioms of the vector space, but the binary operation, the vector additions and scalar multiplication of each of these examples. In this case, we take x1, x2 and y1, y2. Uh, you can add these two ordered pairs, and that is what we call the vector addition. In this manner, the component-wise addition x1 plus y1 and x2 plus y2. This is one possible binary operation defined on R2, and this is the vector addition. The corresponding scalar addition is if you take a C from real numbers, C times x1, x2 is equal to C times x1 comma C times x2. This is what we call scalar multiplication. So with respect to these two operations, this R cross R, or say R2, is a vector space over R. If you take any n copies of this R, say we have n copies here, n copies of R, and it is denoted by R raised to n. Obviously, the corresponding set is x1, x2, etc., comma xn. Okay, each xi comes from this R. So this is a again this is a vector space and denoted by R raised to n. The corresponding operation is if we take two n tuples from this x1, x2, xn and y1, y2, yn, you can define a vector addition as same as above, y1 etc. yn. The vector addition is the component wise addition of its coordinates, that is x1 plus y1 etc., x2 plus y2 etc., n plus yn. So with respect to this, this is a group under addition, a Abelian group under addition. That is the first five axioms of the vector spaces. And now we take a scalar C and multiplied by x1 etc., xn. We can write it as C times x1, C times x2, and so on, C times all the way up to C times xn. So this is the corresponding scalar multiplication in Rn. So if we take R, R square, R2, R3, R4, etc., R raised to n, or in any copies of R, will make a vector space. Another example, so we can consider this is the example 1. This is our example 1. Now we have example 2. Example 2 is nothing but the space of matrices. Okay, so that is denoted by f m by n, where f is a field. So this consists of set of all m by n matrices. This is a m by n, such that A is a m by n matrix whose entry is from, okay, whose entry is from f. This form a vector space again, and the corresponding if a corresponding operations, if a is equal to aij and b is equal to matrix bij, then the corresponding binary corresponding vector addition is defined as a plus b, that is equal to, that is a matrix of same order m by n. Then the corresponding entries are obtained by adding the corresponding entries of a and b. So the ijth entry of a plus b is aij plus bij. This is the vector addition defined on this f m by n. And the corresponding scalar multiplication, C times A is equal to the matrix C times Aij. If you multiply all the entries of A with C, you will get the matrix CA, that is defined to be the scalar multiplication. So this is a nice example. Another example, example 3, this is very important. This is the space of all functions. Space of all functions, that is vector space. Space of all functions defined on a set to a field. Okay, so for this we take a field capital F first, then define V. Define V is equal to set of all F from a set X to F. Okay, such that F is a function. That is the only requirement. Function. Then this is a vector space. With respect to the operations, if we take two functions f and g from V, f plus g to be defined as f plus g of x equal to f of x plus g of x. That is a point-wise addition, and that will act as vector addition. And c times f, that is scalar multiplication. This again should be a function of the same set. So cf of x is defined as c times f of x. Okay, with respect to these two operations, first one is scalar multiplication, vector addition, and the second one is scalar multiplication. With respect to this operation, the set of all functions from any set, there is no relevance for the set x, but the codomain should be a field. Okay, any set x, set of all functions from any set x is a vector space over the field f. Okay, so the corresponding underlying field is f. This is the third example. Now we have two more examples. The other examples are example 4. Example 4. Example 4 is a subset of the space of all functions. If we consider set of all polynomial functions, okay. If you consider set of all polynomial functions over a field. Okay. So if you consider the set of all a0 plus a1 x etc. a n x raised to n, such that ai comes from this f. F is any field. So this form and is denoted by f of x, set of all polynomial expressions. Okay, so this is again a vector space with respect to polynomial addition and scalar multiplication. That is p of x plus q of x. This is the sum of two polynomials p plus q. If p and q are polynomials, then you can add p plus q of x as p of x plus q of x. That is, in general, we can write if p of x is equal to a naught plus a1x plus etc. a n x raised to n, and q of x as b naught plus b1x plus etc. b plus b n x raised to n. You can add this as a naught plus b naught plus a1 plus b1x plus etc. plus an plus bn. That is the sum of corresponding terms of the polynomial. So this is again a vector addition in a set of all polynomial functions. Now the scalar multiplication of this uh, c times p of x equal to c times a naught plus a1x plus etc. a n x raised to n, that is defined to be the usual multiplication of polynomials as c as a constant. C times a naught plus uh, c times a1x plus etc. c times a n x raised to n. So this is the scalar multiplication of this polynomial functions. Then this form a vector space over the corresponding fields. Complex numbers as example 5, and it is denoted by C. C is set of all a plus bi such that a comma b belongs to R. This is again a vector space. If we consider z1 as a plus ib and z2 is c plus di, then the sum z1 plus z2, that is the corresponding sum of the complex numbers, that is a plus c plus c plus d times I, and sorry, a plus c plus b plus d times I. This form a vector addition in set of all complex numbers, and c times z1, that is c or some x times or some k times z1 is equal to k times uh, this a plus I bi, that is equal to ka plus kb times I, and this form as a vector the scalar multiplication of this c. So this form a vector space over c over R. Obviously, this C is a vector space over C itself, but here we can consider the C as a vector space over. If we consider this and example 1 as in example 1 we have discussed R2. If you consider R2 as set of all xy such that x belongs to R and y belongs to R. If you consider this vector space, then you can say that these two vector spaces can be considered as same. Okay, the only difference is if you write the ordered pair x comma y as x plus iy, you can consider that R2 as the C itself. Okay, so this R2 and C are as vector spaces both are same. Okay, so these are the typical examples discussed in section 2.1, and we have one definition here, definition of linear combination. linear combination of linear combination of elements of linear combination of elements of vector space V. For that we consider a vector space V, and the arbitrary elements of vector space is alpha 1, alpha 2, etc., alpha n. So in this textbook, the Greek letters are used to denote the vectors as one English alphabets A, B, C, D, etc. Are used to denote the scalars or elements of F. So if we consider this, you can say that if we consider an element, we know that if any C belongs to F, C times alpha is an element of a this vector space V. So C1 alpha 1, where C1 is an element of F and alpha 1 is an element of V. If we consider this combination C1 alpha 1, C2 alpha 2 plus etc., C and alpha n, this is what we called a linear combination of elements of vector space. elements of V. Okay, so this is the definition, a linear combination of elements of V. This completes the section 2.1. Now we can discuss section 2.2. In that section, we will discuss the basic ideas of subspaces.